Hello everyone. Today we will study the exponential and logarithmic functions. First of all, let me introduce the exponential function. Let a be a positive real number, and let f of x be a to the power of x for all real number x. Then the function f of x is called an exponential function. Next, let me show you some examples. Let f of x be 2 to the power of x, and let g of x be half to the power of x. Graph f of x and g of x by plotting points. Here, function f and function g, they are both exponential functions. Let's graph the functions by plotting points. Let's first of all graph function f. In order to plot points, let's first of all make a table. Make a table for x and f of x. When we plot points, usually pick some positive number and pick some negative numbers. Let's pick -2, -1, 0, 1, and 2. Then plug each number into function f. If I plug in -2, what do I get? If I plug in -2, for f of -2, I get 2 to the power of -2. 2 to the power of -2 is 1 over 2 squared, which is 1 over 4. It's a quarter. So when I plug in -2, I get a quarter. Next, plug in -1. If I plug in -1, I get 2 to the power of -1. That's 1 over 2 to the power of 1, which is half. So if I plug in -1, I get half. What if I plug in 0? If I plug in 0, I get 2 to the power of 0. And we know that 2 to the power of 0 is 1. Every number to the power of 0 is 1. If I plug in 1 for x, 2 to the power of 1 is 2. If I plug in 2 for x, 2 squared is 4. That's the value. Next, let's plot points and sketch graph. First point, -2, 1 over 4. S is -2, y is 1 over 4. Somewhere here. Assume that's 1, 2, 3, 4. -2, 1 over 4, somewhere here. Next point, -1 and half. S is -1, y is half. Somewhere here. Next point, 0, 1. S is 0, y is 1, is here. Next point, 1, 2. S is 1, y is 2, somewhere here. Next point, 2, 4. S is 2, y is 4. Somewhere here. Then, connect these points using a smooth curve. Connect these points using a smooth curve. It looks like this. The curve will be very, very close to 0, but can never be 0, because a positive number raised to any power is always positive. A positive number raised to any power is always positive. So the curve is always above the x-axis. It could be very, very close to 0, but it's always above 0. The curve is very, very close to 0, but it's always above 0. It could be very, very close to 0, but it can never be 0. So that's the graph of the function f of x equal to 2 to the power of x. That's the graph f of x equal to 2 to the power of x. Next, let's graph function g by plotting points. Again, let's make a table for function g. G of x is half of x, half to the power of x. Let's make a table for function g. When we make a table for function g, we pick some positive value for x and some negative value for x. In general, we pick -2, -1, 0, 1, and 2. Then put g of x in the second column. Then plug in -2, -1, 0, 1, and 2 for x. If we plug in -half, -2, what do we get here? For g of -2, we plug in -2 for x. We get half to the power of -2. First of all, we can distribute exponent. We get 1 to the power of -2 over 2 to the power of -2. I can distribute exponent first. When the exponent is negative on the top, I bring to the bottom, make it positive. And when the exponent is negative on the bottom, I bring to the top, make it positive. Then on the top, 2 squared is 4. On the bottom, 1 squared is 1. I get 4. So g of -2 is 4. If I plug in -2, I get 4. Next, plug in -1 for x. Plug in -1 for x. If I plug in -1, I get g of -1. That's half to the power of -1. I can first of all distribute exponent. I get 1 to the power of -1 over 2 to the power of -1. When the exponent is negative on the top, I bring to the bottom, make it positive. And when the exponent is negative on the bottom, I bring to the top, make it positive. On the top, 2 to the power of 1 is 2. On the bottom, 1 to the power of 1 is 1. And 2 over 1 is 2. Next, if I plug in 0, half to the power of 0 is 1. If I plug in 0, I get half to the power of 0. We know that every number to the power of 0 is 1. So if I plug in 0, I get 1. What if I plug in 1? If I plug in 1, for g of 1, I get half to the power of 1. We know that every number to the power of 1 is a number itself. So if I plug in 1, I get half. What if I plug in 2? If I plug in 2, g of 2 is half square. Half square means half times a half. We multiply the top to the top, bottom to the bottom. I get 1 over 4. Next, let's plot the points and sketch the graph. Let's plot the points and sketch the graph. 0, 1, 2, 3, 4. -1, -2, -3, -4. 1, 2, 3, 4. First point is -2, 4. X is -2, y is 4. Somewhere here. Second point is -1, 2. X is -1, y is 2. Somewhere here. Next point is 0, 1. Here. X is 0, y is 1 is here. Next point, 1, half. X is 1, y is half. Somewhere here. X is 1, y is half. Next point, 2, quarter. X is 2, y is a quarter. Somewhere here. Then connect the points using a smooth curve. Connect these points using a smooth curve. It looks like this. here the curve will be very, very close to the x-axis. I can never touch the x-axis because exponential function is always positive. A positive number raised to any power is always positive. So it won't be negative. It won't be 0, it won't be negative. It's always above 0. It could be very, very close to 0, but it's always above 0. So that's the graph for g of x equal to half of x. Next, based on these two graphs, we can see that in function f, if the base is more than 1, then the larger exponent, the larger the value it is. So function f is increasing from left to right. And for function g, if the base is less than 1, then the larger exponent, the smaller it is. The larger exponent, the smaller value it is. So function g is decreasing from left to right. So if the base is more than 1, the graph of an exponential function is increasing from left to right. If the base is less than 1, and the graph is decreasing from left to right. So the exponential function has two types. The graph of an exponential function has two different types. For the exponential function f of x equal to a to the power of x, the graph has two different types. First type, if a is greater than 1, the graph is increasing from left to right. If the base is more than 1, the graph is increasing from left to right. And one tensor here is 1. One tensor here is 1 because any number to the power 0 is 1. If I plug in 0 for x, any positive number to the power 0 is 1. If a is less than 1, and since a must be positive, we say a is between 0 and 1. If a is between 0 and 1, the graph is decreasing from left to right. If a is less than 1, since a is always positive, we say a is between 0 and 1. If a is between 0 and 1, the graph is decreasing from left to right. And the one tensor here is 1, because any positive number to the power 0 is 1. So that's the graph of an exponential function. If a is greater than 1, the graph is increasing from left to right. If a is between 0 and 1, the graph is decreasing from left to right. Now, what if a equal to 1? What if a equal to 1? If a equal to 1, we have f of x equal to 1 to the power of x. And we know that 1 to the power of x equal to 1. That's a horizontal line. That's a horizontal line going through 1. So that's a very special case. We don't consider this case. If a equal to 1, the graph is a straight line, horizontal line going through 1. If a equal to 1, that's a very, very special case. We don't consider this case. We only consider the case that when a is greater than 1 and a is between 0 and 1. So if a is greater than 1, the graph is increasing from left to right. If a is less than 1, the graph is decreasing from left to right. When a equal to 1, that's a very, very special case. We don't consider this case. Now, let's observe both graphs. We can see that in both graphs, their domain is always the set of all real numbers. For both graphs, their domain is always the set of all real numbers, which means all real numbers from negative infinity to infinity. How about their range? Since the entire graph, in both graphs, their entire graph is above the x-axis. So the range is from 0 to infinity. From 0 to infinity. Not including 0. So in both graphs, the range is the set of all values from 0 to infinity. And in both graphs, there are no s-intercepts. the y-intercept is always 0, 1. The y-intercept in both graphs, the y-intercept is always 0, 1. And in both graphs, there's a horizontal asymptote. There's a horizontal asymptote in the x-axis, which is y equal to 0. In both graphs, they have a horizontal asymptote, y equal to 0. X-axis is y equal to 0. The line y equal to 0 is the same as x-axis. It's the same as the x-axis. Now, for the end behavior, if a is greater than 1, for the end behaviors, here we can see that as x approach to negative infinity, function f approach to 0. It's approach from above. Y approach to 0 from above. As s approach to negative infinity, y approach to 0 from above. On the other side, as s approach to infinity, y goes all the way up. So y approach to infinity. Let's call f of x. It's more accurate. As s approach to infinity, f of x also approach to infinity. So as s approach to negative infinity, that means as the curve goes all the way to the left, f of x approach to 0 from above. As s goes all the way to the right, function f goes all the way up, which approach to infinity. That's the end behavior when a is greater than 1. And the end behavior when a is between 0 and 1. It looks like this. On the left side, as s approach to negative infinity, function f goes all the way up, which means f of x approach to infinity. On the other side, as s approach to infinity, that means as the curve goes all the way to the right, function f gets very, very close to 0, but it's a little above 0. So f of x approach to 0 from above. Those are the end behaviors. That's the domain, range, s-intercepts, y-intercepts, horizontal asymptote. And there are no vertical asymptotes. And that's the end behaviors. Next, let me show you some examples. Graph each of the following functions using function transformations. Please indicate the x and y intercepts and asymptotes. First example, f of x is 3 to the power of s plus 1. How can we graph this function? So first step, let's choose the parent function. For the parent function, drop number 1 here. It looks like f of x equal to 3 to the power of x. That's the parent function. For the parent function here, base 3 is larger than 1. Base 3 is larger than 1. So its graph looks like this. It's increasing from left to right. If base is more than 1, the function is increasing from left to right. So the graph of the parent function looks like this. That's the parent function. Y-intercept is 1, and horizontal asymptote is y equal to 0. That's the parent function. Next, when we add 1 to x, we shift the graph 1 unit to the left. When we add 1 to x, we shift the graph 1 unit to the left. So when we graph y equal to 3 to the power of s plus 1, when we add 1 to x, we shift the graph 1 unit to the left. Shift this graph 1 unit to the left. The new graph looks like this. If I shift this graph 1 unit to the left, this point becomes 1, 1. That's the new graph. And that's the graph of this function f of x. When we shift the graph 1 unit to the left, the horizontal asymptote stays the same. The horizontal asymptote stays the same. It's also y equal to 0. If I shift the graph to the left and right, the horizontal asymptote stays the same. And here we can see that in this graph there's no s-intercepts. For the y-intercept, we plug in 0 for x. For the y-intercept, we plug in 0 for x. For the y-intercept, plug in 0 for x. Set s equals 0. I get y equal to f of 0. Which is 3 to the power of 0 plus 1. We plug in 0 for x. And 0 plus 1 is 1. We get 3 to the power of 1, which is 3. So the y-intercept is 0, 3. There are no s-intercepts. Horizontal asymptote is y equal to 0. That's how we graph this function. Next example. F of x is 4 to the power of x minus 2 plus 3. F of x is 4 to the power of x minus 2 plus 3. In order to graph this function, let's first of all choose the parent function. For the parent function, you can drop number 3, drop negative 2. What's left is 4 to the power of x. So we choose 4 to the power of x as a parent function. This is an exponential function. Since the base is more than 1, the function is increasing from left to right. This is an exponential function. Since the base is more than 1, the graph of this function is increasing from left to right. So it looks like this. That's the parent function. The horizontal asymptote is a line y equal to 0. That's an x-axis. The y-intercept here is 1. Next, let's do some transformation to match this function. If we subtract 2 from x, we shift the graph 2 units to the right. If we subtract 2 from x, we shift the graph 2 units to the right. So shift the graph 2 units to the right. I get y equal to 4 to the power of s minus 2. The graph looks like this. Shift this graph 2 units to the right. This point 0, 1 become 2, 1. And we know that if we shift the graph from left to right, the horizontal asymptote stays the same. The horizontal asymptote stays the same. So the horizontal asymptote is also y equal to 0. Next, when I add 3 to the function, I shift the graph 3 units upward. So next, I shift the graph 3 units upward. When I shift the graph 3 units upward, I add 3 to the function. I get y equal to 4 to the power of x minus 2 plus 3. I shift this graph 3 units upward. When I shift the graph upward, the horizontal asymptote will be shifted at the same time. When I shift the graph upward, the horizontal asymptote will be shifted at the same time. So that's 0, 1, 2, 3. The horizontal asymptote will be shifted up by 3 units. It will be here. That's the new horizontal asymptote. That's the new horizontal asymptote. It was y to the power of 0. It was y equal to 0. If I shift it 3 units upward, it becomes y equal to 3. That's the new horizontal asymptote. The graph shifts up by 3 units, looks like this. This point, it was 2, 1. If I shift up by 3 units, it will be 2, 4. That's the graph of this function. And this is function f. This is function f. In this graph, we can see that the horizontal asymptote is y equal to 3. There are no s-intercepts. There are no s-intercepts. There is a y-intercept here. There's a y-intercept here. For y-intercept, we set s equal to 0. For y-intercept, we set s equal to 0. Then plug in 0 for x. Plug in 0 for x. I get y equal to f of 0, which is 4 to the power of 0 minus 2 plus 3. 0 minus 2 is negative 2. We get 4 to the power of negative 2 plus 3. 4 to the power of negative 2 can be written as 1 over 4 squared plus 3. 1 over 4 squared can be written as 1 over 16. 3 can be rewritten as 3 over 1. Next, find the least common multiple of the denominator. For 16 and 1, the least common multiple is 16. So, for 3 over 1 here, I multiply top and bottom by 16. It's 1 over 16 plus 48 over 16, which is 49 over 16. So the y-intercept is 0, 49 over 16. So that's the y-intercept here. 0, 49 over 16. That's the y-intercept. And for exponential function, the domain is always a set of all real numbers. So the domain is a set of all real numbers from negative infinity to infinity. And for this function, the range is a set of all real numbers from 3 to infinity. Since the horizontal asymptote is 3, the range is a set of all real numbers from 3 to infinity. In the previous example, the domain of the exponential function is always a set of all real numbers. So the domain is a set of all real numbers from negative infinity to infinity. And the range, since the horizontal asymptote is 0, the range is a set of all integers, all real numbers from 0 to infinity. The range is a set of all real numbers from 0 to infinity, not including 0. Next example. Graph of the function f of x equal to 1/3 to the power of x minus 2. First of all, let's choose the parent function. In order to choose the parent function, usually you drop the numbers. Let me drop -2. If I drop -2, I get 1/3 to the power of x. That's the parent function. Here, for the parent function, since the base is less than 1, the graph is decreasing from left to right. The graph is decreasing from left to right. If the base is less than 1, the graph is decreasing from left to right. So the parent function looks like this. It's decreasing from left to right. That's the graph. And for exponential function, the y-intercept is always 1. The y-intercept is always 1. And the horizontal asymptote is always y equal to 0. That's the y-intercept. That's the horizontal asymptote. Next, if we subtract 2 from the function, we shift the graph 2 units downward. If we subtract 2 from the function, we shift the graph 2 units downward. So here we shift the graph 2 units downward. If we shift the graph 2 units downward, the horizontal asymptote will be shifted at the same time. Horizontal asymptote, it was 0 here. If I shift the graph 2 units downward, it becomes -2. That's the new horizontal asymptote. That's the new horizontal asymptote. If I shift the 2 units downward, it becomes y equal to -2. It was y equal to 0 here. If I shift the 2 units downward, it becomes y equal to -2. This point here is 1. If I shift the 2 units downward, it becomes -1. And that's the y-intercept. Then the graph stays the same shape. That's the horizontal asymptote. That's the graph. Y equal to 1/3 to the power of x minus 2. In this graph, you can see that the y-intercept is 0, -1. There's an s-intercept here. What's an s-intercept? In this graph, there's an s-intercept here. What's an s-intercept? For s-intercept, we set y equal to 0, then solve an equation for x. For s-intercept, we set y equal to 0, then solve an equation for x. So here, set y equal to 0. For s-intercept, we set y equal to 0. So I set 0 equal to 1/3 to the power of x minus 2. If I add 2 to both sides, that means 2 equal to 1/3 to the power of x, which is the same as saying 1/3 to the power of x equal to 2. How can we solve the equation for x here? Here I can apply ln to both sides. Apply ln to both sides. I get ln of 1/3 to the power of x equal to ln of 2. Next, I can bring x to the front. I get x times ln of 1/3 equal to ln of 2. Then I can divide both sides by ln of 1/3. S equal to ln of 2 over ln of 1/3. That's x. That's an s-intercept. So for s-intercept, the y-coordinate is always 0. So we write ln of 2 over ln of 1/3, comma 0. That's an s-intercept. That's an s-intercept. This point here is ln of 2 over ln of 1/3. That's an s-intercept. And horizontal asymptote is y equal to -2. The horizontal asymptote is y equal to -2. And for this graph, the domain is always a set of all real numbers. For exponential function, the domain is always a set of all real numbers. So here, the domain is a set of all real numbers from -infinity to infinity. What's the range? Since the horizontal asymptote is y equal to -2, the range is from -2 to infinity. The set of all real numbers from -2 to infinity, not including -2. That's the domain and range. Next example. F of x equal to 1/4 to the power of x plus 2 plus 1. How can we graph this function? Let's first of all choose the parent function. For the parent function, let's first of all drop the numbers. We drop number 1, drop number 2. What's left is 1/4 to the power of x. We can take this as a parent function. Y equal to 1/4 to the power of x. This is an exponential function, and the base is less than 1. If the base is less than 1, the graph is decreasing from left to right. If the base is less than 1, the graph is decreasing from left to right. That's the graph of the parent function. And for exponential function, the y-intercept is always 1. The horizontal asymptote is always y equal to 0. Next, based on the parent function, let's try to graph function f. In order to graph function f, we first of all add 2 to x. If we add 2 to x, we shift the graph 2 units to the left. If we add 2 to x, we shift the graph 2 units to the left. So first of all, shift the graph 2 units to the left. First of all, shift the graph 2 units to the left. If I shift the graph 2 units to the left, the horizontal asymptote stays the same. This point 0, 1 will be -2, 1. and the graph stays in the same shape. When we shift the graph to the left, horizontal asymptote stays the same. So the horizontal asymptote is still y equal to 0. That's the graph of the function 1 over 4 to the power of x plus 2. When we add 2 to x, we shift the graph 2 units to the left. Next, we need to add 1 to the function. If we add 1 to the function, we shift the entire graph 1 unit upward. So next, I shift the graph 1 unit upward. Shift this graph 1 unit upward. The horizontal asymptote was y equal to 0 here. If I shift it 1 unit upward, I need to shift the asymptote at the same time, so it becomes y equal to 1. That's the new horizontal asymptote. It's y equal to 1. That's the new horizontal asymptote. And this point here is negative 2, 1. If I shift it up by 1 unit, it becomes negative 2, 2. If I shift this point up by 1 unit, it becomes negative 2, 2. It's here. That's one of my key points. That's negative 2, 2. And then draw the graph in the same shape. Draw the graph in the same shape. That's a graph. In this graph, we can see that there's no x-intercepts. The y-intercept is here. There's a y-intercept here. For y-intercept, we set s equal to 0. For the y-intercept, set s equal to 0. Plotting 0 for x, find y. So set s equal to 0. If I set s equal to 0, I have y equal to f of 0, which is 1 over 4 to the power of 0 plus 2 plus 1. That's 1 over 4 squared plus 1. 1 over 4 squared means 1 over 4 times 1 over 4. That's 1 over 16. And number 1 can be rewritten as 1 over 1. Then find the common denominator. Here for 16 and 1, the least common multiple is 16. In order to make 1 to be 16, I multiply top and the bottom by 16. So I get 1 over 16 plus 16 over 16, which is 17 over 16. That's the y-intercept, 17 over 16. And for the y-intercept, x coordinate is always 0. So I get 0, 17 over 16. For y-intercept, we set s equal to 0. So y equal to f of 0, which is 1 over 4 to the power of 0 plus 2 plus 1. Here I get 17 over 16. That's the y-intercept. And the horizontal asymptote is y equal to 1. The horizontal asymptote is y equal to 1. For exponential function, the domain is always the set of all real numbers. The domain is the set of all real numbers from negative infinity to infinity. For this function here, since the horizontal asymptote is y equal to 1, the range is the set of all real numbers from 1 to infinity. The range is the set of all real numbers from 1 to infinity. Since the horizontal asymptote is 1, the range is the set of all real numbers from 1 to infinity. Next example, graph the function f of x equal to negative e to the power of x plus 3. In order to graph this function, let's first of all choose the parent function. For the parent function, we drop negative sign. Drop number 3, we get e to the power of x. So take y equal to e to the power of x as a parent function. Here, e is an Euler number. E is about 2.718. So e is more than 1. If e is more than 1, the exponential function is increasing from left to right. If e is more than 1, exponential function is increasing from left to right. So the graph looks like this. It's increasing from left to right. Since e is more than 1, e is about 7.18, it's 2.718. And for exponential function, the y-intercept is always 1, and the horizontal asymptote is always y equal to 0. If the base is e, this exponential function has a name. It's called a natural exponential function. If the base is e, this exponential function is called a natural exponential function. That's a very, very special case. If the base is e, this exponential function is called a natural exponential function. That's a very, very special case. If the base is e, that's called a natural exponential function. Next, observe this function here. We have a negative sign in the front. If we add negative sign in the front of the function, we flip the graph over the x-axis. If we add negative sign to the front of the function, we flip the graph over the x-axis. So we flip the graph over the x-axis. If I add negative sign to the front, I flip the graph over the x-axis. If I flip over x-axis, positive 1 becomes negative 1, but the horizontal asymptote stays the same. Positive 1 becomes negative 1, but the horizontal asymptote stays the same. If I flip the graph over the x-axis, positive 1 becomes negative 1, but the horizontal asymptote stays the same. So the horizontal asymptote is still y equal to 0. That's the graph of y equal to negative e to the power of x. If I add negative sign to the front of the function, I flip the graph over the x-axis. Next, when we add 3 to the function, we shift the graph 3 units upward. So we shift the graph 3 units upward. When we shift the graph, we must shift the horizontal asymptote at the same time. The horizontal asymptote was y equal to 0. If I shift it 3 units upward, it becomes y equal to 3. 1, 2, 3. So that's the new horizontal asymptote. That's the new horizontal asymptote. Y equal to 3. That's the new horizontal asymptote. And this point is negative 1. If I shift up by 3 units, negative 1 plus 3 is positive 2. It's here. This point come here. if I shift this point up by 3 units, -1 plus 3 is +2. This point is here. Then draw the graph in the same way. The graph stays the same shape, so draw the graph in the same way. That's the graph of this function. Y equal to -e to the power of x plus 3. That's the graph. And then in this graph, we can see that the y-intercept is 0, 2. The y-intercept is 0, 2. There's the s-intercept here. How can we find s-intercept? There's s-intercept here. How can we find s-intercept? For s-intercept, we set y equal to 0. For s-intercept, we set y equal to 0. Solve the equation for x. So for s-intercept, we set y equal to 0. If we set y equal to 0, we get 0 equal to -e to the power of x plus 3. I can move -e to the power of x to the left side. If I move this term over, it's negative. When I move over, it becomes positive. I get e to the power of x equal to 3. Next, in order to solve for x, I apply ln to both sides. I get ln of e to the power of x equal to ln of 3. Then on the left side, by the property of logarithmic function, ln of e to the power of x equal to x. So I get s equal to ln of 3. So for the s-intercept, we have ln of 3, 0. For the s-intercept, the y-coordinate is always 0. And x is ln of 3. Y-coordinate is always 0. So I get ln of 3, 0. That's an s-intercept. This point here is ln of 3. That's an s-intercept. And the horizontal asymptote is y equal to 3. For exponential function, the domain is always a set of all real numbers. For exponential function, the domain is always a set of all real numbers, from -infinity to infinity. Here, since the horizontal asymptote is y equal to 3, and the graph is decreasing from left to right here, it's decreasing from left to right. The range is a set from -infinity to 3. The range is a set of all real numbers from -infinity to 3. Since the horizontal asymptote is 3, and the graph is going downward from left to right. So it's from -infinity to 3. The range is a set of all real numbers from -infinity to 3. Next, graph of the function f of x equal to 6 equal to e to the power of -x minus 2. Graph of the function f of x equal to e to the power of -x minus 2. In order to graph this function, let's first of all choose the parent function first. For the parent function, we drop all numbers. If we drop -2 and drop negative sign in front of x, I choose y equal to e to the power of x. I choose y equal to e to the power of x as a parent function. Again, if the base is e, that's called a natural exponential function. If the base is e, this function has a name. It's called a natural exponential function. It's called a natural exponential function. That's a very, very special case. If the base is e, that's called a natural exponential function. And since e is greater than 1, so the graph is increasing from left to right. Since e is greater than 1, the graph is increasing from left to right. And for exponential function, the y-intercept is always 1, and the horizontal asymptote is always y equal to 0. Now, when we try to graph function f, if I make x from positive to negative, I flip the graph over the y-axis. If I change x from positive to negative, I flip the graph over the y-axis. So this piece come here. This piece go to the other side. If I flip the graph over the y-axis, horizontal asymptote stays the same. It's still y equal to 0. And the y-intercept also stays the same. It's still 1. I flip the graph over the y-axis. So this piece come here. This piece go to the other side. That's e to the power of negative x. Here I flip the graph over the y-axis. Next, when we subtract 2 from the function, we shift the graph 2 units downward. When we subtract 2 from the function, shift the graph 2 units downward. Since the horizontal asymptote is y equal to 0, if I shift the graph 2 units downward, it becomes y equal to 2, y equal to negative 2. That's the new horizontal asymptote, y equal to negative 2. That's the new horizontal asymptote. And this point is 1. If I shift it down by 2 units, it becomes negative 1. So 1 becomes negative 1 if I shift it down by 2 units. Next, draw the graph with the same shape. The graph stays the same shape. And for this graph, we can see that the y-intercept is negative 1. The y-intercept is 0, negative 1. There's the s-intercept here. How can we find the s-intercept? For the s-intercept, we set y equal to 0. For the s-intercept, set y equal to 0. f of x is y. Set y equal to 0. We get 0 equal to e to the power of negative x minus 2. Next, we try to isolate e. So I can add 2 to both sides. I get 2 equal to e to the power of negative x. Next, in order to solve for e, I apply ln to both sides. I get ln of 2 equal to ln of e to the power of negative x. Then left side stays the same. On the right side, by the property of logarithmic function, ln e of negative x is negative x. Because ln of e of x is always x. So ln of e of negative x is negative x. Next, in order to get s by itself, I multiply both sides by negative 1. In order to get s by itself, I multiply both sides by negative 1. So I get s equal to negative ln of 2. So that's an s-intercept. Negative ln of 2, 0. So s-intercept is negative ln of 2, 0. So that's an s-intercept here. Negative ln of 2. That's an s-intercept. And the horizontal asymptote is y equal to negative 2. The horizontal asymptote is y equal to negative 2. Horizontal asymptote is y equal to negative 2. For the domain and range, this is exponential function. For exponential function, the domain is always the set of all real numbers. from net infinity to infinity. And for the range, since the horizontal asymptote is -2, the range is in the set of all real numbers from -2 to infinity. Since the graph is above -2, the range is the set of all real numbers from -2 to infinity. That's the domain and range. Next, let me introduce the logarithmic function. Let a be a positive number and a not equal to 1. Let f of x equal to log base a of x for all positive real number x. Then f of x is called a logarithmic function. Next, let's look at some examples. Let f of x be log base 2 of x, and let g of x be log base of half of x. Graph f of x and g of x by plotting points. So let's graph the functions by plotting points. Let's graph function f first. Let's first of all make a table for x and f of x. For logarithmic function, in order to plot points, let's choose some special points. Let's choose 1/4, 1/2, 1, 2, and 4 for log base 2 of x. Because this number are related to base of 2. Next, find f of x. Based on this x, find f of x. If I plug in 1/4, what's log base 2 of 1/4? This equation is asking 2 raised to what power is 1/4? Is 2 raised to what power is 1/4? We know that 1/4 can be rewritten as 1/2 squared. And 1/2 squared can be rewritten as 2 raised to -2. Then by matching left side and right side, you can see that s equal to -2. Next, plug in 1/2 for x, find f of x. If I plug in 1/2 for x, I get log base 2 of 1/2. Log base 2 of 1/2 is asking 2 raised to what power equal to 1/2. Then by matching left side and right side, you can see that 1/2 can be rewritten as 2 raised to -1. So x must be -1. So that means log base 2 of half is -1. Next, plug in 1 for x. I get log base 2 of 1. Log base 2 of 1 is asking 2 raised to what power is 1. We know that 2 to the power of 0 is 1. So s must be 0. That's 0 here. Next, if I plug in 2 for x, I get log base 2 of 2. What's log base 2 of 2? We know that 2 to the power of 1 is 2. So log base 2 of 2 is 1. If I plug in 4 for x, what's log base 2 of 4? What's log base 2 of 4? Log base 2 of 4 is asking 2 raised to what power is 4? And we know that 2 to the power of 2 is 4. So log base 2 of 4 is 2. Next, based on these points, sketch a graph. First point, s is 1/4, y is -2. S is 1/4, y is -2, somewhere here. Second point, s is 1/2, y is -1, somewhere here. 1/2, y is -1, somewhere here. Next point, x is 1, y is 0. That's here. Next point, x is 2, y is 1. X is 2, y is 1. Next point, x is 4, y is 2. Then connect all these points using a smooth curve. The graph looks like this. Since x can only be positive real numbers, x cannot touch 0. Since x can only be positive real numbers, the graph cannot touch 0, cannot touch the y-axis. So that's a vertical asymptote. The curve can be very, very close to the y-axis, but can never touch y-axis. That's a vertical asymptote. So the vertical asymptote is s equal to 0. That's the graph of function f, log base 2 of x. Next, let's graph function g by plotting points. For function g, let's make another table. Put x and g of x on the table. Since here the base of g is 1 over 2, let's choose some number. For x, let's choose some number related to half. We can use the same number here. 1 over 4, 1 over 2, 1, 2, and 4. 1 over 4, 1 over 2, 1, 2, and 4. Let's choose some number related to base of half. Then based on this x, find g of x. First of all, I plug in 1 over 4 for x. In function g, plug in 1 over 4 for x. If I plug in 1 over 4 for x, what do we get? We get log base 1 over 2 of 1 over 4. So here it's asking log half raised to what power is 1 over 4? Half raised to what power is 1 over 4? Here we can see that half squared is 1 over 4. So s is 2. So s is 1 over 4, g of x is 2. Next, plug in 1 over 2 for x. Plug in 1 over 2 for x. We get log base of half. Log base half of a half equal to what? What's log base half of half? This log is asking a half raised to what power is a half? A half raised to what power is a half? We know that half raised to power 1 is half. So this logarithm equal to half, equal to 1. Half raised to power 1 is half. The power is 1. That means s is 1. Log base 2 of half equal to 1. Next, plug in 1 for x. Plug in 1 for x. If we plug in 1 for x, we get log base half of 1. Here the question is asking a half raised to what power is 1? We know that half raised to power 0 is 1. So log base half of 1 must be 0. Next, plug in 2 for x. Plug in 2 for x. If we plug in 2 for x, we get log base half of 2. What's log base half of 2? This question is asking a half raised to what power is 2? A half raised to what power is 2? We know that 1 over 2 can be rewritten as 2 to the power of negative 1. And 2 by itself is 2 to the power of 1. Then by matching left side and right side, you can see that negative 1 times s equal to 1. Divide both sides by negative 1. S equal to negative 1. That means half to the power of negative 1 is 2. So log base half of 2 is negative 1. Next, plug in 4 for x. Plug in 4 for x. If we plug in 4 for x, we get log base half of 4. So the question is asking a half raised to what power is 4? A half raised to what power is 4? Let's assume the unknown power is x. we know that 1 over 2 can be rewritten as 2 raised to negative 1. And 4 can be rewritten as 2 squared. Then, by matching the left side and right side, by matching the exponent, we know that negative 1 times s equal to 2. Then I can divide both sides by negative 1. I get s equal to negative 2, which means a half to the power of negative 2 is 4. So log base 2 of 4 is half, is negative 2. Log base half of 4 is negative 2. Then, based on this point, sketch the graph. Let's plot the points. First point, s is 1 over 4, g of x is 2. Somewhere here. Next point, s is half, y is 1. Somewhere here. Next point, s is 1, y is 0. Next point, s is 2, y is negative 1. Next point, s is 4, y is negative 2. It's here. Then, connect the points using a smooth curve. Since s can only be positive real number, the curve doesn't touch the y-axis, but it could be very, very close to the y-axis. So the y-axis is a vertical asymptote. Connect the points using a smooth curve. That's the graph of the function y equal to g of x, and g of x is log base half of x. The vertical asymptote is the y-axis, which is s equal to 0. And that's the graph y equal to f of x. That's log base 2 of x. So here we can see that if the base is more than 1, the logarithmic function is increasing from left to right. And if the base is less than 1, the graph of logarithmic function is decreasing from left to right. In both graphs, the vertical asymptote is the y-axis, which is s equal to 0. And the s-intercept is 1, 0. S-intercept is 1, 0. There are no y-intercepts. Since s can only be positive real number, the curve cannot touch the y-axis. There's no y-intercepts. Next, let me show you the graph of the general logarithmic functions. F of x equal to log base a of x. Here, let's consider two cases. If a is greater than 1 or a is less than 1. Case 1. If a is greater than 1, then the graph is increasing. The y-axis is the vertical asymptote. The graph is increasing from left to right. And the s-intercept is 1. If a is less than 1, and of course a must be positive, so if a is between 0 and 1, the graph is decreasing from left to right. And the y-axis is the vertical asymptote. In both graphs, 1 is an S-intercept. So that's the graph of the logarithmic function. If a is greater than 1, the graph is increasing from left to right. If a is less than 1, the graph is decreasing from left to right. So for a logarithmic function, domain is the set of all positive real numbers from 0 to infinity. The domain is the set of all positive real numbers from 0 to infinity. The range is the set of all real numbers from negative infinity to infinity. It goes all the way up. On the left side goes all the way down. On the right side goes all the way up. For the other graph, on the left side goes all the way up. On the right side goes all the way down. So the range is always the interval from negative infinity to infinity. There are no y-intercepts. There are no y-intercepts. In both graphs, there are no y-intercepts. And in both graphs, the s-intercept is 1, 0. The s-intercept is the point 1, 0. And in both graphs, there's a vertical asymptote in y-axis. In both graphs, the y-axis is a vertical asymptote. The y-axis is the equation s equal to 0. So in both graphs, the vertical asymptote is the y-axis, which is a line s equal to 0. Next, let's describe the end behaviors for both graphs. If a is greater than 1, as s approaches to 0, here 0 cannot be negative. So as s approaches to 0 from the right side, the function f of x approaches to negative infinity. That's the end behavior on the left side. On the right side, as s approaches to infinity, f of x goes all the way up. F of x goes all the way up to infinity. So that's the end behavior. On the left side, x doesn't go to negative infinity because the domain is the set of all positive real numbers. So on the left side, s can only approach to 0. And it's a little greater than 0. It's not exactly 0. X is a little greater than 0. So as s approaches to 0 from the right, f of x approaches to negative infinity. And in the case where a is between 0 and 1, the end behavior looks like this. On the left side, as s approaches to 0 from the right, this little plus here means limit from the right, s approaches to 0 from the right. Here, as s approaches to 0 from the right, the curve f of s goes all the way up. So f of s approaches to infinity. On the other side, as s approaches to infinity, on the right side, as s approaches to infinity, f of s goes all the way down. So f of x approaches to negative infinity. That's the end behavior of the logarithmic function. Next, let's do some examples. Graph each of the following functions. Using function transformation. using function transformation. Please indicate the x and y intercepts. And vertical asymptotes. First example, f of x is log base 3 of s minus 2. F of x is log base 3 of s minus 2. How can we graph this function? First step, let's choose the parent function. In order to choose the parent function, we drop 2 here. If I drop 2 here, I get log base 3 of x. I get log base 3 of x. So I choose log base 3 of x as a parent function. So for the parent function, I choose y equal to log base 3 of x. Here, since the base is greater than 1, the curve of the logarithmic function is increasing from left to right. Since the base is greater than 1, the curve of the logarithmic function is increasing from left to right. So the graph of a parent function looks like this. S-intercept is 1, and the vertical asymptote is the line s equal to 0. Next, if we subtract 2 from x, we shift the graph 2 units to the right. If we subtract 2 from x, we shift the graph 2 units to the right. So shift the graph 2 units to the right. If I shift the graph 2 units to the right, the vertical asymptote will be shifted at the same time. If we shift the graph 2 units to the right, the vertical asymptote will be shifted at the same time. The vertical asymptote it was s equal to 0. If I shift it 2 units to the right, it will be s equal to 2. So that's the new vertical asymptote. S equal to 2. This point is 1. If I shift it 2 units to the right, it will be 3. 1 plus 2 is 3. Then draw the graph in the same shape. That's the graph of a function y equal to log base 3 of x minus 2. In this graph, we can see that there's no y-intercepts. S-intercept is 3. So there are no s-intercepts, no y-intercepts. S-intercept is 3, 0. And the vertical asymptote is s equal to 2. The vertical asymptote is s equal to 2. That's the vertical asymptote. Now, for this graph, the domain is a set of all real numbers from 2 to infinity. Since the vertical asymptote is 2, the domain is a set of all real numbers from 2 to infinity. The domain of all real number domain is the set of all real numbers from 2 to infinity. And for logarithmic function, the range is always the set of all intervals, all real numbers from negative infinity to infinity. For logarithmic functions, the range is always the set of all real numbers from negative infinity to infinity. That's a domain and that's a range. Next example, graph of function f of x equal to log of x plus 1 plus 2. How can we graph this function? For a logarithmic function, if there's no base, we assume the base is 10. This is called a common logarithmic function. If there's no base, we assume the base is 10. That's called a common logarithmic function. If the base is 10, that's called a common logarithmic function. That's a special case. If there's no base, we assume the base is 10. That's called a common logarithmic function. In order to graph this function, let's first of all choose a parent function. For the parent function, we can drop all the numbers. If I drop 2 and drop 1, the parent function is log of x. The parent function is log of x. And for log of x, if there's no base, we assume the base is 10. When the base is greater than 1, the graph of the logarithmic function is increasing from left to right. If the base is greater than 1, the graph of the logarithmic function is increasing from left to right. So that's the graph of the parent function. And for the logarithmic function, s-intercept is always 1, and the vertical asymptote is always s equal to 0. That's the y-axis. That's the vertical asymptote. That's the s-intercept. Next, based on the parent function, if I add 1 to x, I shift the graph 1 unit to the left. If I add 1 to x, I shift the graph 1 unit to the left. If I shift this graph 1 unit to the left, the vertical asymptote will be shifted at the same time. It was 0 here. If I shift it 1 unit to the left, it becomes s equal to -1. So the new vertical asymptote is -1, s equal to -1. That's the new vertical asymptote, s equal to -1. This point is 1 here. If I shift it 1 unit to the left, it becomes 0. This point becomes 0. So that's the graph y equal to log of x plus 1. And the graph stays the same shape. That's the graph when we shift it 1 unit to the left. Next, when we add 2 to the function, we shift the graph 2 units upward. When we add 2 to the function, we shift the graph 2 units upward. if we shift this graph 2 units upward, the vertical asymptote stays the same, but this point 0 will be 2. The vertical asymptote stays the same at -1. This point will be shifted up by 2 units. It becomes 2. Then the graph stays the same shape. That's the graph of the function y equal to log of s plus 1 plus 2. And then based on the graph, we can see that the y-intercept is 0, 2. There is an s-intercept here. There is an s-intercept here. In order to find s-intercept, we set y equal to 0, solve for x. In order to find s-intercept, we set y equal to 0 and solve an equation for x. So set y equal to 0. For s-intercept, set y equal to 0. I get 0 equal to log of x plus 1 plus 2. In order to get s by itself, I can first of all subtract 2 from both sides. I get -2 equal to log base 10. Log by itself, if there's no base, what's on the base is 10. So I get log base 10 of s plus 1. So subtract 2 from both sides. I get -2 equal to log base 10 of s plus 1. That can be rewritten as log base 10 of s plus 1 equal to -2, which means 10 to the power of -2 equal to s plus 1. That means 10 to the power of -2 equal to s plus 1. That's the definition of logarithmic function. That means this log here means 10 to the power of -2 equal to s plus 1. Then here, 10 to the power of -2 can be rewritten as 1 over 10 squared. 1 over 10 squared. 10 squared is 100. Next, we can subtract 1 from both sides. We get 1 over 100 minus 1 equal to x. And number 1 can be rewritten as 1 over 1. The common denominator here is 100, so we can multiply top and bottom by 100, which is 1 over 100 minus 100 over 100. Then subtract the numerator. 1 minus 100 is 99. It's -99. We get -99 over 100 equal to x. That's the s-intercept. So the s-intercept is -99 over 100, 0. For the s-intercept, the y-coordinate is always 0. So this point here is -99 over 100. The s-intercept here is -99 over 100. That's an s-intercept. Here we can see that the vertical asymptote is the line s equal to -1. The vertical asymptote is the line s equal to -1. The domain is the set of all real numbers from -1 to infinity. Since that's the vertical asymptote, the domain is the set of all real numbers from -1 to infinity. And for logarithmic function, the range is always the set of all real numbers. For logarithmic function, the range is always the set of all real numbers from -infinity to infinity. Next example. How can we graph the function? F of x equal to log base 1/3 of x minus 3. How can we graph the function? Log base 3 of x minus 3. So in order to graph the logarithmic function, let's first of all choose the parent function. For the parent function, you can drop number 3. We get log base 1/3 of x. So we choose the parent function to be y equal to log base 1/3 of x. Here, since the base is less than 1, the graph of the logarithmic function is decreasing from left to right. Since the base is between 0 and 1, the graph of the logarithmic function is decreasing from left to right. So the graph of the parent function looks like this. That's the graph of the parent function. S-intercept is 1. Vertical asymptote is the y-axis, which is s equal to 0. That's the parent function. Next, if we subtract 3 from the entire function, we shift the graph 3 units downward. Shift the graph 3 units downward. If I shift the graph up and down, the vertical asymptote stays the same. If I shift the graph up and down, the vertical asymptote stays the same. So the vertical asymptote is still s equal to 0. But for this point here, for this key point here, if I shift it 3 units downward, it becomes 1, comma, negative 3. This key point here becomes 1, comma, negative 3. So this is 1, this is negative 3. This point becomes 1, comma, negative 3. And the vertical asymptote stays the same shape. Then let's sketch the graph in the same shape. This point will be shifted here. That's the graph of the logarithmic function, y equal to log base 1/3 of x minus 3. We shift this graph 3 units downward. Now, for this graph, we can see that there's no y-intercept. There's s-intercept here. So there are no y-intercepts. There is a s-intercept. For an s-intercept, we set y equal to 0. Solve the equation for x. So we set y equal to 0. For the s-intercept, set y equal to 0. We get 0 equal to log base 1/3 of x minus 3. In order to solve this equation for x, I can first of all add 3 to both sides. If I add 3 to both sides, I get 3 equal to log base 1/3 of x. Next, solve an equation for x. This equation, 3 equal to log base 1/3 of x, it can be rewrite as log base 1/3 of x equal to 3. By the definition of logarithm, this expression, it means 1/3 to the power of 3 equal to x. By the definition of logarithm, this expression means 1/3 to the power of 3 equal to x. Then solve for x. 1/3 to the power of 3 means 1/3 times 1/3 times 1/3, which is 1/27. So the s-intercept is 1/27. And for the s-intercept, the y-coordinate is always 0. So this point here is 1/27. That's the s-intercept. And the vertical asymptote is s equal to 0. The vertical asymptote is s equal to 0. The domain is a set of all real numbers from 0 to infinity. Since the vertical asymptote is s equal to 0, the domain is a set of all real numbers from 0 to infinity. And for the logarithmic function, the range is always the set of all real numbers from negative infinity to infinity. The range is always a set of all real numbers from negative infinity to infinity. Next example. Graph the function f of x equal to log base 1/4 of s plus 2 plus 1. Graph the function of f of x equal to log base 1/4 of s plus 2 plus 1. In order to graph this function, let's first of all choose the parent function. In order to choose a parent function, we can drop number 1, drop number 2. What's left is log base 1/4 of x. Log base 1/4 of x. That's the parent function. Y equal to log base 1/4 of x. That's the parent function. Since the base is 1/4, which is less than 1, the graph of a parent function is a logarithmic function, decreasing from left to right. Since the base is 1/4, which is less than 1, the graph of a logarithmic function is decreasing from left to right. That's the graph of a parent function. The s-intercept is 1. Vertical asymptote is the y-axis, which is a line s equal to 0. That's the parent function. Now here we can see that if we add 2 to x, we shift the graph 2 units to the left. So I first of all shift the graph 2 units to the left. If I shift this graph 2 units to the left, the vertical asymptote it was 0. If I shift it 2 units to the left, it becomes -2. The vertical asymptote it was s equal to 0. If I shift it 2 units to the left, it becomes s equal to -2. That's the new vertical asymptote. S equal to -2. If I shift the graph 2 units to the left, I must shift the asymptote at the same time. So the new vertical asymptote is s equal to -2. This point here, it was 1. The key point here was 1. If I shift it 2 units to the left, it becomes -1. That's the key point. That's the key point. If I shift this point 2 units to the left, it was 1 here. If I shift it by 2 units, it becomes -1. Then sketch a graph in the same shape. That's a graph of y equal to log base 1 over 4 of x plus 2. Then draw the graph in the same shape. Next, when I add 1 to the function, I shift the graph 1 unit upward. Next, I shift the graph 1 unit upward. Next, shift the graph 1 unit upward. When I shift a logarithmic function up and down, the vertical asymptote stays the same, but the key point will be changed. If I shift the graph 1 unit up, this point becomes -1, 1. So the key point will be changed. Vertical asymptote stays the same. The key point will be shifted up by 1 unit. It becomes -1, 1. That's the key point here. Next, draw the graph in the same shape. That's the graph of the function y equal to log base 1 over 4 of x plus 2 plus 1. In this graph, there's an x-intercept and there's a y-intercept. In order to find the x-intercept, we set y equal to 0. For the x-intercept, I set y equal to 0. For the x-intercept, set y equal to 0. I get 0 equal to log base 1 over 4 of x plus 2 plus 1. Next, solve the equation for x. Here I can first of all subtract 1 from both sides. If I subtract 1 from both sides, I get -1 equal to log base 1 over 4 of x plus 2, which means log base 1 over 4 of x plus 2 equal to -1. Then by the definition of logarithm, it means 1 over 4 to the power of -1 equal to x plus 2. This logarithm means 1 over 4 to the power of -1 equal to x plus 2. Now, what's 1 over 4 raised to -1? I can first of all distribute exponent to the fractions. I get 1 to the power of -1 over 4 to the power of -1. When the exponent is negative, we can move 1 from top to the bottom, make exponent positive. I can move 4 from bottom to the top, make it exponent positive. So you get 4 to the power of 1 over 1 to the power of 1, which is 4. So I get 4 equal to x plus 2. Then I can subtract 2 from both sides. I get s equal to 2. So the x-intercept is 2, 0. The x-intercept is 2, 0. So this point here is 2. It's 2, 0. That's the x-intercept. For the y-intercept, we set x equal 0 and find y. Set x equal to 0 and find y. For the y-intercept, set x equal to 0. If I set x equal to 0, plug in 0 for x, y equal to f of 0, which is log base 1 over 4 of 0 plus 2 plus 1. I get log base 1 over 4 of 2 plus 1. Now let's evaluate log base 1 over 4 of 2. What's log base 1 over 2? Log base 1 over 4 of 2. What's log base 1 over 4 of 2? This logarithm is asking 1 over 4 raised to what power is 2? 1 over 4 raised to what power is 2? So this logarithm is asking 1 over 4 raised to what power is 2? We know that 1 over 4 can be rewritten as 1 over 2 squared. And 1 over 2 squared can be rewritten as 2 raised to negative 2. X is exponent. Leave it there. Number 2 by itself is 2 to the power of 1. Since the base is the same, the exponent must be the same. We get negative 2x equal to 1. Then divide both sides by negative 2. S equal to negative 1 over 2. So here, log base 1 over 4 of 2 is negative 1 over 2. So y equal to negative 1 over 2 plus 1. Negative 1 over 2 plus 1 is 1 over 2. So the y-intercept is 1 over 2. This point here is 1 over 2. For the y-intercept, the x-coordinate is always 0. And here we can see that the vertical asymptote is a line s equal to negative 2. That's the vertical asymptote. The domain here, since the vertical asymptote is negative 2, the domain is a set of all real numbers from negative 2 to infinity. The domain is a set of all real numbers from negative 2 to infinity. And for logarithmic function, the range is always a set of all real numbers from negative infinity to infinity. For logarithmic function, the range is always from negative infinity to infinity. Next example. How can we graph the function f of x equal to ln of negative x minus 2? How can we graph the function f of x equal to ln of negative x minus 2? In order to graph this function, let's first of all choose the pattern function. For the pattern function, we drop negative 2, drop negative sign. We get f of x equal to ln of x. For the pattern function, drop negative 2, drop negative sign in the front. We get ln of x. That's a pattern function. And we know that ln of x is the same as log of base e of x. ln of x is the same as log base e of x. Here the base is e. E is about 2.718, which is more than 1. So the graph of a logarithmic function, is increasing from left to right. This e is more than 1. The graph of a logarithmic function is increasing from left to right. Here the x-intercept is 1, and the vertical asymptote is the line s equal to 0. In the case when the base is e, ln of x is called the natural logarithmic function. ln of x is called a natural logarithmic function. That's a very, very special case. y equal to L, f of x equal to ln of x. That's called a natural logarithm function, logarithmic function. That's called a natural logarithmic function. That's called a natural logarithmic function. When the base is e, that's called a natural logarithmic function. Since e is greater than 1, the graph of a logarithmic function is increasing from left to right. Next, if I make x from positive to negative, if we change x from positive to negative, we flip the graph over the y-axis. If we change x from positive to negative, we flip the graph over the y-axis. So I first of all flip the graph over the y-axis. If I flip this graph over the y-axis, positive 1 becomes negative 1 here. And the vertical asymptote stays the same. When I flip the graph over the y-axis, positive 1 becomes negative 1. And the vertical asymptote stays the same. Vertical asymptote stays the same. It's s equal to 0. When I flip the graph over the y-axis, positive 1 becomes negative 1. Then draw the mirror image of this graph. It looks like this. Next, when I subtract 2 from the function, I shift the entire graph 2 units downward. When I subtract 2 from the entire function, I shift this graph 2 units downward. That's the graph y equal to ln of negative x. When I subtract 2 from the entire function, I shift the graph 2 units downward. So this point becomes negative 1, negative 2. This point becomes negative 1, negative 2. And the vertical asymptote stays the same. If I shift the graph up and down, the vertical asymptote stays the same. So next, I shift the graph 2 units downward. The key point is here. Negative 1, negative 2. That's the key point. And the vertical asymptote stays the same. We draw the graph in the same shape. Let me draw the graph here. Draw the graph the same shape. Draw this graph the same shape. That's the graph of the function y equal to ln of negative x minus 2. In the graph here, you can see that there's no y-intercept. There's no y-intercept. But there's an s-intercept here. There's an s-intercept here. So there are no y-intercepts. There's an s-intercept. For s-intercept, we set y equal to 0. Set y equal to 0. Solve an equation for x. For s-intercept, set y equal to 0. Solve an equation for x. If I set y equal to 0, I get 0 equal to ln of negative x equal minus 2. 0 equal to ln of negative x minus 2. In order to solve an equation for x, I can first of all add 2 to both sides. If I add 2 to both sides, I get 2 equal to ln of negative x. Next, in order to get s by itself, I apply e to both sides. I get e squared equal to e to the power of ln of negative x. Then, by the property of logarithm, e cancels ln. We get negative x on the right side. So e squared equal to negative x. Then I can multiply both sides by negative 1. I get s equal to negative e squared. I get s equal to negative e squared. So that's an s-intercept. That's an s-intercept. Negative e squared. That's an s-intercept. Negative e squared. So s-intercept is negative e squared comma 0. For the s-intercept, the y-coordinate is always 0. And the vertical asymptote here is s equal to 0. The vertical asymptote is s equal to 0. For the domain, since the vertical asymptote is 0, here the domain is from negative infinity to 0. The domain is a set of all real numbers from negative infinity to 0. The domain is a set of all real numbers from negative infinity to 0. For logarithmic function, its range is always from negative infinity to infinity. For logarithmic function, its range is always a set of all real numbers from negative infinity to infinity. Next example. Graph of the function f of x equal to negative ln of x plus 3. Graph of the function f of x equal to negative ln of x plus 3. In order to graph this function, let's first of all choose the parent function. For the parent function, we can drop number 3 here. Drop negative sign in the front. We get ln of x. So the parent function is y equal to ln of x. ln of x is the same as log of base e of x. If the base is e, that's called a natural logarithmic function. If the base is e, that's called a natural logarithmic function. That's a very, very special case. If the base is e, that's called a natural logarithmic function. That's called a natural logarithmic function. Here, base is e. E is approximately 2.71a, which is more than 1. If the base is more than 1, the graph of the logarithmic function is increasing from left to right. If the base is more than 1, the graph of the logarithmic function is increasing from left to right. So that's the graph of the parent function. S-intercept is 1, and the vertical asymptote is the line s equal to 0. That's the graph of the parent function. Next, if I add negative sign in the front of the function, I flip the graph over the s-axis. If I add negative sign in front of the entire function, I shift the graph over the s-axis. So flip the graph over the s-axis. If I make the entire function negative, I flip the graph over the s-axis. So let's graph the function y equal to negative ln of x. I flip the entire graph over the s-axis. If I flip the graph over the s-axis, the vertical asymptote stays the same. And this point 1 also stays the same here. Then flip the graph over the s-axis. It looks like this. That's a graph when I flip the graph over the s-axis. Next, when I add 3 to x, I shift this graph 3 units to the left. When I add 3 to x, I shift this graph 3 units to the left. Next, I shift the graph 3 units to the left. If I shift the graph 3 units to the left, the vertical asymptote will be shifted at the same time. The vertical asymptote was s equal to 0 here. If I shift it 3 units to the left, it becomes negative 3. It becomes s equal to negative 3. It was 0. It was s equal to 0 here. If I shift it 3 units to the left, it becomes s equal to negative 3. That's the new vertical asymptote. That's the new vertical asymptote. And this point is 1. If I shift it 3 units to the left, it becomes negative 2. That's the key point. Next, draw the graph the same way it is. Draw the graph in the same shape. It looks like this. That's a graph of the function y equal to negative ln of x plus 3. In this graph, you can see that the s-intercept is negative 2, 0. The s-intercept is negative 2, 0. For the y-intercept, here, we plug in 0 for x. For the y-intercept, set s equal to 0. For the y-intercept, set s equal to 0. I get y equal to f of 0, which is negative ln of 0 plus 3. And we know that 0 plus 3 is 3. So the y-intercept is negative ln of 3. The y-intercept is negative ln of 3. And for the y-intercept, the s-coordinate is always 0. We got 0, comma, negative ln of 3. It's here. let's call this point negative ln of 3. That's the y-intercept. That's the x-intercept. That's the y-intercept. And the vertical asymptote is s equal to negative 3. For the domain, since the vertical asymptote is negative 3, the domain is a set of all real numbers from negative 3 to infinity. The domain is a set of all real numbers from negative 3 to infinity. The range for logarithmic function, the range is always a set of all real numbers. For logarithmic function, the range is always a set of all real numbers. So the range is a set of all real numbers from negative infinity to infinity. Next, let me introduce compound interest. Let's consider the following situation. When $P is deposited with an annual interest rate of R, assume the interest is generated at the end of the year. Find the following. First of all, let's try to find the amount after 1 year. For the amount after 1 year, we need to compute the principal plus the interest. For the amount after 1 year, they equal to the principal plus the interest. The principal is $P. We deposit $P. And what's the interest? For the interest, it's the principal times the annual interest rate. That can be rewritten as P times 1 plus R. So the amount after 1 year is the principal times 1 plus the interest rate. Now, how can we compute the amount after 2 years? How can we compute the amount after 2 years? For the amount after 2 years, do the same thing. We take our new principal times 1 plus interest rate. We know that for the amount after 1 year, we have the principal times 1 plus the interest rate. So for the amount after 2 years, we take the new principal times 1 plus the interest rate. Here the new principal is P times 1 plus R. That's a new principal. P times 1 plus R. That's a new principal after 1 year. After 1 year, that's a new principal. Times 1 plus the interest rate. In the second year, interest rate stays the same. It's also R. That can be rewritten as P times 1 plus R squared. So similarly, based on the same pattern, the amount after n years, the amount after t years, let's say t, amount after t years, usually we use t to represent time. Amount after t years it will be P times 1 plus R to the power of n. That's the amount after t years. So, if the principal $P is deposited with an annual interest rate of R, then the amount after t years will be P times 1 plus R to the power of t. The amount after t years will be P times 1 plus R to the power of t. Here, in the beginning of the problem, we assume the interest is generated at the end of each year. Now, what if the interest is generated at the end of each month? What's the amount after t years? What if the interest is generated at the end of each month. Instead of each year, or if the interest is generated at the end of each month instead of each year, then what's the principal? What's the amount after t years? What's the amount after t years? If the interest is generated at the end of each month, then we can use the same formula. Here the principal stays the same, but here R is the interest rate for 1 year. A year has 12 months, so the interest rate for each month will be R over 12. Interest rate for each month will be R over 12. This is the annual interest rate. A year has 12 months, so the interest rate for each month will be R over 12. Now, if we calculate the interest once a year, there are T periods. Now, if we calculate the interest monthly, that means there are 12 periods in 1 year. So in T years, it will be 12 times T periods. In 1 year, we calculate the interest 12 times. So in T years, we calculate interest 12 times T times. So that's the amount after T years. If the interest is generated at the end of each month, that's the amount after T years. If the interest is generated at the end of each month. Now, or if the interest is generated at the end of each day. Or if the interest is generated at the end of each day. Or if the interest is generated at the end of each day, then in this situation, the amount after T years, the principal stays the same. R is the annual interest rate. So for each day, we take annual interest rate divide by 365. For each day, for the daily interest, we take the annual interest divide by 365. Then on each year, we calculate the interest 365 times. On each year, if we calculate the interest once a day, in a year we calculate the interest 365 days, 365 times in a year. And in T years, we calculate the interest 365 times T times. That's the amount of T years if we calculate the interest once a day. So, in general, if the interest is compound n times a year, if the interest is compound n times a year, that means we calculate the interest n times a year. then the amount after t years is a of t, amount after t years, equal to the principal times 1 plus r over n to the power of n times t. Here, n represents number of times we calculate the interest in a year. So, if the interest is compounded n times in a year, the amount after t years will be a of t equal to p times 1 plus r over n to the power of nt. That's the formula for compound interest. That's formula for compound interest. Keep this formula in mind. Next, let's consider a very, very special case, an extreme case. Let's consider extreme case, a very, very extreme case. What if the interest is calculated continuously? What if the interest is compound continuously? Means we calculate the interest every second, every moment. What if we calculate the interest every second, every moment? Which means n approaches to infinity. Which means n approaches to infinity. We calculate the interest every second, every moment, and become very, very large number. What's the amount after t years? Now, in order to find a formula for the amount after t years, let me first of all show you a formula. As n approaches to infinity, the formula 1 over n to the power of n approach to e. Keep this formula in mind. You will see the proof in your calculus class, but for now, let's keep this formula in mind. As n approaches to infinity, 1 plus 1 over n to the power of n approach to e, the Euler number. As n approaches to infinity, 1 plus 1 over n to the power of n approach to e. Keep this formula in mind. Based on this formula, we will find a formula for the amount after t years if we compound interest continuously. Keep this formula in mind. You will learn a proof for this formula in your calculus class. But for now, keep this formula in mind. As n approaches to infinity, as n becomes very, very large, 1 plus 1 over n to the power of n approach to e. Based on this formula, we can calculate the amount after t years if we compound interest continuously. Now, let me rewrite this formula. A of t equal to p times 1 plus r over n to the power of nt. If we compare this formula with this part, they look very, very similar. So we try to make one substitution here. I want to let r over n equal to 1 over m. I want to let r over n equal to 1 over m. I try to rewrite this formula. Looks like this. Then I can use this formula. So keep this formula in mind. You will learn a proof in your calculus class. But for now, memorize this formula. We'll use this formula to find a formula for the compound interest as n approaches to infinity. So here we try to make r over n equal to 1 over m, which means if I cross multiply, m must be r times m. Which means if I cross multiply, then n equal to r times m. Next, substitute. Let n equal to r over m. Let n equal to r times m. Substitute. Let n equal to r times m. I get r over r times m, n equal to r times m times t. If I simplify, I have 1 plus 1 over m. Then r times m times t can be rewritten as power m times r times t. And then apply this formula. As n approaches infinity, since r is constant, m also approaches infinity. From this formula, n equal to r times m, we know that m can be rewritten as m can be rewritten as 1 over r times n. And we know that as n approaches infinity, m also approaches infinity. As n approaches infinity, m also approaches infinity. As n approaches infinity, m equal to a constant times infinity is also infinity. Therefore, as m approaches infinity, 1 plus 1 over m to the power of m equals to e. 1 plus 1 over m to the power of n equal to e. As m approaches infinity. Same thing here. As m approaches infinity, 1 plus 1 over m to the power of m is e. So a of t equal to p to the power of e to the power of rt. As m approaches infinity. So that's the formula for the compound interest if the interest is compound continuously. So keep these two formulas in mind. This formula and this formula. That's a formula for compound interest. And that's for compound interest if the interest is compound continuously. That's the formula for compound interest. If the interest is compound finitely many times in a year, we use this formula. If the interest is compound continuously, we use this formula. Next, let's create an example. When $4,000 is invested at an annual interest rate of 6%, find the amount after 10 years if the interest is compounded: part A, annually; part B, semi-annually; part C, quarterly; part D, monthly; part E, daily; F, continuously. Annually means we compound interest once a year. Semi-annually, that means we compound interest twice a year. Quarterly means we compound interest 4 times a year. Monthly means we compound interest 12 times a year. Daily means we compound interest 365 times a year. Continuously means we compound interest infinitely many times a year. So let's answer each question individually. For part A, if we compound interest annually, means we compound interest once a year. So n is 1. Here in this formula, P represents the principal. That's the money invested. Here P is 4,000. P is the principal. That's the money invested. Here P is 4,000. R is the annual interest rate. R is the annual interest rate. Here R is 6%. 6% converted to decimal number is 0.06. If we convert 6% to decimal number, that's 0.06. We divide 6 by 100. That's 0.06. T represents number of years. In this formula, t represents number of years. Here, t is 10 years. In this problem, t is 10 years. And n represents the number of times in which the interest will be compounded in a year. N represents the number of times that the interest will be calculated in a year. The interest will be compounded in a year. N represents the number of times that the interest is compounded in a year. So for part A, if the interest is compounded annually, means we compound interest once a year. So n equal to 1. In part A, n equal to 1. So plug in the amount after 10 years. The amount after 10 years is P times 1 plus R over N. Here R is 0.06 over N, N is 1, to the power of NT. That's 1 times 10. Then use calculator for this number. Type this to the calculator. I get $7,163.33. For money, round to 2 decimal places. For money, round to 2 decimal places. Part B, if the interest is compound semi-annually, means we compound interest twice a year. So n is 2. If n is 2, plug into this formula. The amount after t years is 4,000 times 1 plus R over N. Here R is 0.06, N is 2, to the power of NT. For part B, N is 2, T is 10. Then type this to the calculator. Use calculator, I get $7,224.44. For money, round to the nearest cents. Part C, if the interest is compound quarterly, means the compound interest 4 times a year. So n equal to 4. Plug in. A equal to P times 1 plus R over N to the power of NT. Here P is 4,000. 1 plus R over N. R is 0.06. N is 4. To the power of NT. To the power of NT. Here N is 4. T is 10. Then use calculator. I get 7,256.07. For money, round to the nearest cents. Part D, if the interest is compound monthly, means we compound interest 12 times a year. N equal to 12. For part D, N equal to 12. It means we compound interest 12 times a year. Then plug in A equal to P times 1 plus R over N. R is 0.06. N is 12. To the power of 12 times 10. Then use calculator. I get 7,277.59. For monies, round to the nearest cents. Part E, compound daily. That means we compound interest 365 times a year. Assume this is not leap year. In general, we assume a year has 365 days. Assume that's not a leap year. So the amount is 4,000 times 1 plus 0.06 over 365. That's R over n. To the power of nt, here n is 365, t is 10. Then use calculator. I get $7,288.11. For money, 1 to the negative cents. Part F, compound continuously. If we compound continuously, we use this formula. Part F, if we compound interest continuously, we use this formula. So for part F, since the interest is compound continuously, we use the formula that A of t equal to p to the power of e, p times e to the power of rt. Here the principal is 4,000. E is a constant. R is 0.06. T is 10. Then use calculator. I get $7,288.48. For money, 1 to the negative cents. That's the answer for F. That's the answer for F. If we compound interest continuously. Now, part G. In the above example, if the interest is compounded continuously, if the interest is compounded continuously, how long will we take the amount to reach $10,000? How long will we take the amount to reach $10,000? If the interest is compounded continuously, how long will we take the amount to reach $10,000? Now here we know that the amount is 10,000. The amount is 10,000. Principal stays the same. Principal is 4,000. Annual interest rate is 6%. We're looking for T. We're looking for time. How long will we take the amount to reach 10,000? So, since it's compound continuously, we use this formula. Amount equal to the principal times e to the power of rt. Plug in the numbers, solve the equation for t. Plug in the numbers, solve the equation for t. Here, amount is 10,000. Principal is 4,000 times e to the power of rt. Here, r is 0.06. We don't know t. We're looking for t. So, in order to solve an equation for t, I can first of all divide both sides by 4,000. If I divide both sides by 4,000, I get 10,000 over 4,000 equal to e to the power of 0.06 times t. Here on the left side, 10,000 divided by 4,000, I get 2 over 2.5. Or we can leave it as 5 over 2. Equal to e to the power of 0.06 times t. Next, in order to solve for t, I apply ln to both sides. I get ln of 5 over 2 equal to ln of e to the power of 0.06 times t. Then on the right side here, by the property of logarithm, ln cancels e. I get 0.06 times t. So ln of 5 over 2 equal to 0.06 times t. Next, in order to solve for t, I can divide both sides by 0.06. So t equal to ln of 5 over 2 over 0.06. Then here I use my calculator. In my calculator, t is about 15.27 and t is measured in years. It takes about 15.27 years. Here t is measured in years. So it takes about 15.27 years. Next example, when 25,000 is invested at annual interest rate of 3.25%, find the amount after 8 years if the interest is compound per A annually, per B semi-annually, per C quarterly, per D monthly, per E daily, F continuously. So let's first of all write down the given information first. Here the principal is 25,000. R is the annual interest rate, which is 3.25%. 3.25%. A quarter is in a sense 0.25. A quarter is 0.25. 3.25% can be written as 0.0325. So the annual interest rate is 0.0325. Time is 8 years. For part A, if an interest is compound annually, means we compound interest once a year, A equal to 1. We compound interest once a year, A equal to 1. Apply the formula. Amount equal to principal times 1 plus R over N. Here R is 0.0325. N is 1 to the power of NT. Here N is 1. T is A. Then multiply. Here I use my calculator. I get $32,289.44. That's the amount after 8 years. Part B. If the interest is compound semi-annually, that means we compound the interest twice a year. So in part B, N equal to 2. Use the same formula. Amount is the principal times 1 plus R over N. Here R is 0.0325. N is 2. To the power of NT. Here N is 2. T is A. Then use calculator. In my calculator, I get $32,355.56. That's what I get in my calculator. In general, for money, round to 2 decimal places, round to the nearest cents. Part C. If the interest is compound quarterly, that means N equal to 4. A year has 4 quarters, N equal to 4. The formula is amount equal to principal times 1 plus R over N. R is 0.0325. N is 4 to the power of NT. N is 4. T is A. Then use calculator. I get $32,389.21. Part D. Compound monthly. If the interest is compound monthly, that means N equal to 12, because a year has 12 months. So the amount is principal times 1 plus R over N. Here R is 0.0325. N is 12. To the power of nt, here N is 12, T is A. Then use calculator. In my calculator, I get $33,411.86. Part E, compound daily. Names with compound interest once a day. One compound interest 365 times a year. So for part E, N equal to 365. So the amount here is principal times 1 plus the annual interest rate 0.0325 over 365 to the power of 365 times A. Then use calculator. Here I get $32,422.88. Part F, compound continuously. For continuously compound interest, continuously compound interest, the formula is A of t equal to P times e to the power of RT. Then plug in. The amount is the principal, 25,000 times e to the power of RT. R is 0.0325. T is A. So I get 0.0325 times A. Then use calculator. In my calculator, I get $32,423.25. For monthly, 1 to the nearly cents. Now, part G. In the above example, if the interest is compounded continuously, how long will we take the amount to reach 40,000? How long will we take? How long will we take the amount to reach 40,000? So for part G, we know that the initial principal is 25,000. Annual interest rate is 0.0325. The amount is 40,000. Amount will eventually reach 40,000. We are looking for T. We try to find out how long does it take. How long will it take the amount to grow to 40,000? So plug into this formula. A is 40,000. Plug into this formula. For continuously compound interest, plug into this formula. The amount A is 40,000. Principal is 25,000. E stays the same. R is 0.0325. We don't know T. we are looking for t. In order to solve the equation for t, I can first of all divide both sides by 25,000. So I get 40,000 over 25,000 equal to e to the power of 0.0325 times t. Then here on the left side, 40,000 divided by 25,000, if you simplify, you get a over 5. That equal to e to the power of 0.0325 times t. Next, in order to solve the equation for t, I can apply ln to both sides. If I apply ln to both sides, I get ln of a over 5 equal to ln of e to the power of 0.0325 times t. Then on the right side, by the property of logarithms, ln cancels e. We get 0.0325 times t. On the left side, leave it the way it is. It's ln of a over 5. Then, in order to get t by itself, I use ln of a over 5 divided by 0.0325. Here I divide both sides by 0.0325. Then use calculator. Take ln of a over 5, divide by 0.0325. In my calculator, I get 14.46 years. T is measured in years. So it takes about 14.46 years to grow to 40,000.